нужно нам сделать, да? Воспользуюсь. Так, вот мой микрофон мигает, значит он меня чувствует. Окей, это хорошо. Так, ладно, ну я попробую, потом тогда посмотрим, что из этого выйдет. Окей. Так, ну что, давайте традиционно. Turn into English. Okay. So we continue our discussion of some general topics. So let me just give a small reminding about what we're speaking about. So it was the previous lecture, as you remember. So we started with some general picture about this, the general description of the world with quantum physics. Yes, so we have this Hilbert space. We have these two basic abstractions, observables and states, which gives us probability distribution. And actually, in our previous lecture, we considered the first part. We considered these states. Yes, and we discussed this stuff about Hilbert spaces, basic axioms of Hilbert spaces. We considered this topic of cat states, which cat state is just a vector, as we discussed. Yes, and that so we have these pure states. Yes, and actually pure state is an array of these vectors. So it's like a vector times some phase vector, which can be arbitrary. However, if we consider this this construction psi, like cat bra, yes, so it's invariant under this phase vector, and so it's a useful way to describe states. And finally, we came to this concept of block vector. Yes, so using this block sphere in order to describe our pure states. So the small reminding about which I missed last time is just about handwriting of this stuff. So you know, sometimes people when people write this kind of expressions, people write it like psi like this, and sometimes people ask something, what the hell is going on? What is letter X means here? So it's not a letter X. Yes, it's just cat and bra. And but usually I will. So it's a bit faster to write, but I usually try to write in this way, because for me my consciousness usually when my consciousness see this text, it's interpreted as really as letter X. So sometimes it's not very convenient. But by the way, so for example, Jacob Biamonte from Skoltech, he likes to write in this way. So just small note, okay. So next we move to the next topic. It's a topic is what so it's I will just maybe copy it from here. Yep. So the next topic it's observables. Okay. Let me move it let me move it like here. Okay. So it's a topic 1.2.3. Yep. Yep.
На школе был такой вопрос, не помню уже, кому из лекторов, наблюдаемая величина и измеряемая величина — это одно и то же?
Or I think for all practical purposes, it's the same one. So, for example, in English we have these observables, and I don't know what is the difference. Measurables and observables. Well. So sometimes people introduce some observables like abstract mathematical constructions, which are useful, really useful. However, we still do not know how it actually can be measured experimentally, for example. So, for example, in quantum cryptography, we assume that Eve can do anything which do not contradict quantum mechanics, and so she can measure every what we call observable. However, we do not know how it really can be measured. Maybe this difference, kind of difference. Okay. So, nevertheless, so here we just we'll speak about what is called observable. So sometimes people call it phone name and measurement. It's a very fundamental concept. So the basic idea is that observable in quantum mechanics, it's some, again, some abstraction, which is described with Hermitian operator. Yep. Hermitian operator, remember, it means that if we consider its Hermitian conjugate, it gives us back our operator. And just also to note that in this science, this quantum information, people usually do not use these hats in contrast to like traditional quantum mechanics. It's like just convention, because all the things usually are operators. So in this science, people usually do not need to distinguish between, let's say, classical values and corresponding operators, like classical coordinate and operator of coordinate. So all are operators, so no hats. It's okay. Again, so Hermitian, so it means that we make this Hermitian conjugate. So it, again, it's transpose plus complex conjugate, and so we can say that if we take our operator, yes, we put it inside this phi and psi cat and phi bra, yep, phi cat, and just distinguish, just swap them. Then we need to put this this complex conjugate. Okay. The next important point about this Hermitian operators is that we need to introduce the eigenvectors and the eigenvalues. Okay, so it's the general form. Yes, so remember that eigenvector. So you act with the operator on our eigenstate, obtain some value, the value called eigenvalue. As far as as you remember, every eigenvector can be defined up to some constant, because if you put, like, say, I put some constant c here and put constant c here, actually c times psi I, so it's also an eigenvector, of course. And usually when people think about eigenvectors of operators, they use this normalization condition just to make things more simple. Okay. Well, some basic properties of eigenvalues and eigenvectors. So let me copy it from here. So what is so the first basic property of eigenvalues is that all eigenvalues are real. Yes, so this is like a corollary of the fact that our operator is Hermitian. Yes. The second very important property is that all eigenvectors they are orthogonal to each other. Yes, so this is just standard Kronecker symbol. Yes, and so the number of eigenvectors is given by the dimension of our space. So if we consider all the eigenvectors, they are all orthogonal to each other, and actually they form what I said here. So what is called a full or complete, yes, complete basis in our Hilbert space. Okay. Another very important point about these Hermitian operators, let me remove it. It's what is called a spectral decomposition. This is this form. So you see that any operator, any Hermitian operator, can be written in such a form. So where again this psi i's and lambda I is eigenvectors and eigenvalues. Okay, and so actually it's very important form of decomposing any Hermitian operator. Yeah. Actually, nope, because so you see that if we write our operator in this, so what does it mean? This form, it means that any Hermitian operator can be written in a diagonal form, like lambda1, lambda2, blah blah blah, lambda d, in the basis of psi i's. And actually, okay, you can think about it as a Jordan normal form, but it's trivial. Yes, so you do not have this complex like this ones, this Jordan blocks and whatever.
Прям даите различия для разных вот условия, которые дает, что вот именно вот.
Just a second. It's just so it's a feature of these Hermitian matrices. So every Hermitian matrices have these nice features. So it's very special form of matrices. Okay, and that is why. So it has these properties. And so the second question was what about?
Can this construction be generalized to infinite dimensional spaces?
Actually,
Function analysis that not in each situation this operator can be decomposed, or it can be really hard to decompose it to
honestly, I don't remember because I do not like infinite dimensions.
Wait, do you know that you're muted?
I'm muted. Muted. Actually, muted. This computer is muted, and it's okay, I think. Well, so it's okay. Well, so any other questions? So about the difference between eigen. So each eigenvalue have different.
Ну, что для всех лямбда различные.
For each.
Для, ну, типа для разного и все.
Actually, not the case. So for example, let's say, so maybe some example. So for example, basic example. For example, you have this identity operator. Identity operator. So you see that it has two eigenvalues here, let's say, and it has an arbitrary number of eigenvectors. So actually you can choose some subspace where you have this.
Well, maybe I can answer a question why there is no Jordan blocks. Because you know, you can make an unitary transformation, yeah, and unitary transformed Hamiltonian is still Hermite.
Yes.
So you can just imagine you made such diagonalization that there are Jordan blocks.
Okay.
But each Jordan block is not Hermite.
Actually, yeah.
Yeah, because you transform Jordan block with a lambda 1 0. You transform it and you get lambda and 0 1 in left. Yeah.
Okay. So as far as I remember, the Jordan form has this unitaries. So here I have my Jordan matrix, the Jordan form, and here I have some two unitaries.
Yeah.
Okay, and actually, yes. So it's not Hermitian.
Yeah. Each
because each Jordan block is not Hermitian because it's not symmetrical. Okay, thank you. Well, it's a kind of okay. Thank you. Well, so we have this abstraction. We have this Hermitian matrices. We say that okay, I have Hermitian matrices. They describe my measurement, and now we need to understand how actually it describes it. Okay, and let me just write it. Okay, so what does it mean? So imagine we have some particle, some quantum object, and it's in a pure state, which we say, okay, I describe my pure state with some vector of psi. Okay, and then I say, okay, I measure my state psi with some measurement, and I say that this measurement is described by this Hermitian operator. Okay, and let's say, okay, my O. Let me also write it here. So I consider it in a way that it has this spectral decomposition. Okay, this psi i's. Okay, and I measure it. So what do I obtain? So, and here there is again very fundamental concept is what is called a Born rule, and it's just axiomatics. And axiomatics says me the following: that in each measurement I obtain some value. Okay, so I see something on my, let's say, screen of my measurement device, and the rule is the following: that on the screen of my device I always see some eigenvalue. So I see some lambda I, let's say. Okay, so it's some classical value which I observe actually, and the rule says that the probability that I see this value lambda I is given by psi I. Oh, sorry. So it's given by actually, okay. So for pure states, it's given by psi I squared. Okay, so it's given by, let's say, overlap, yes, between the eigenvector which corresponds to this lambda I, yes, and my initial state psi. Okay, and important point which I missed is the following: that actually, if we move back to this case where we have a number of eigenvectors and they have let's say different. So I have different eigenvectors, but they have the same eigenvalue, and it means that we can. So on the one hand, I can use this kind of decomposition, but if I, let's say, take all different eigenvalues, yes, and move all the eigenvectors which correspond to this eigenvalue to the same like bracket, so I can obtain something like this. So I said that my I goes to, okay, so I here goes to from 1 to D, where this is my dimension of my space, and here I said that my I goes to some from 1 to D with tilde, and here I have this lambda I pi. So what does it mean? So look, so here, let's say this lambda I can be the same, and with this lambda I tilde, I say all different, and this pi's is just a set of this eigenvalues with some indices. Okay, plus etc. So does it clear, or so maybe I should just a second. So let me copy paste my original handwriting. Okay, up. So what does it mean?
Why don't you choose just psi I as projector rate?
You will see in a moment. I'm sorry that I missed this point. Okay, so again, so what do we have? This, so we have this initial decomposition. Then I take all distinct lambda i's and denote it with this lambda I tilde, and move all the corresponding terms into one term, and so this term appears to be what is called projector. And remember, so projector means that if I multiplied it, so I take two different projectors, then if they are the same, they just give me the same pi. Yes, if they're different, they just give me 0. And the thing which I actually missed is the following: that what I obtain in this where? Nope. So there is no any sum. So there is so nope. So I choose some pi. Yes, I choose some pi j. Yep. And here I obtain my Kronecker symbol. So if they're the same, they shows just one. If they're different, they just zero. Okay, and then I think.
Просто у вас справа 3 индекса, а слева 2.
Sorry, where you see. So where you see 3 indices? I'm sorry, maybe I missed something. So no, it's not Einstein summations. Nope.
The question is, what the general concept was. For example, I have chosen a wrong basis here, where too many psi i's or what. And so you said that there were d lambda i's.
Yep.
Yeah? And then you said it's too much. I choose only m of them. Yeah.
Yep. So the reason is the following. Let me just explain. So if I go to my, let me write it. Sorry for this mess. So what we have? So we have this measurement, okay? And what I actually obtain, I obtain lambda, this one, because so and it's important. And so I have this particle in state psi, okay? And I obtain this sum of these distinct, let's say distinct eigenvalues, and the probability with which I obtain this distinct eigenvalue is given by, so probability of this lambda I with tilde is given by this construction, this psi, pi, psi. Okay, so in the case where this projector is just a projector on some psi I with a, like, let's say a single term. Okay, yeah. In this case I actually obtain so what I have, so I have this psi I, yeah. And this is just psi I model square. Okay, so it's standard form. However, if I have some similar so I have the same eigenvalue with different eigenvectors, I should it's really actually it's important that here is this projector.
Okay. Can you turn to the previous formula or the definition of pi? Yeah. I mean, there is sum over from I1 to m. M is bigger than d or
so
or not. So you say that here eigenvalue can be repeatable.
Yes, of course. So sorry. Yeah, of course. Okay. So of course, this what here I called d with tilde. Of course, it's less or equal than d, of course.
Bigger or less? You're bigger.
Sorry. Yep. Like this. Yeah.
Okay.
Of course, because you compress your expression, because some of them are the same. So I just put it over brackets. Okay. So.
The probability of lambda tilde.
Yep.
Somehow bigger or equal to probability of lambda.
Yes, of course. So here, what we have here, so you need to like to obtain the overlap between your state and the space which is spanned by for example 2, 3, or 4 eigenvectors. Okay, and of course this probability will be larger, of course.
So it's probability of projection on this subspace.
Yep. So this is the basic idea.
But when we measure something, we measure with this probability of with the first probability.
No. So the
with that probability of projection.
So this is the final rule is the following. Okay, and this is what is called the Born rule. Okay. So we after measurement we obtain this lambda I with tilde. Okay, and sometimes people ask a question. So, and what about the state? Yes. So what is the state after measurement? So in this, what is called von Neumann measurement is a special case of measurement. And in this kind of measurement, the resultant state which you obtain after this kind of after state after measurement is given by let me maybe just copy paste it. Boom, 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 boom. Dun, dun, dun. Well, it's a kind of complicated stuff. Boom, boom. So let me move it here. So the resulting, yes, it's not very convenient actually. So the resulting state, which you obtained after your measurement, is given by this expression. So what we have? So you see that. So we take our initial state. We take this state psi. Okay. Then we act with this projector, and here where it's very important that this is actually this projector which is compound, which consists of all these eigenvalues which corresponds to this eigenvalue. Okay, so you act with this projector on the initial state, and then you divide it by this this expression in the bottom. So it's just to obtain a good normalization condition. So it's just to obtain this psi times psi equal to 1. Okay, and this is what is called collapsed state. So we say, so people say that the state after the measurement is collapsed. Okay, so any questions? So what?
Почему это общитое с волной, а не общитое?
So the difference between psi I, so the first answer is because, again, so look, in this pi, actually, I can have like several, like psi I1 plus psi I2 plus, etc. In the case where I have some lambda eta, lambda i's with tilt, because there maybe the number of different eigenvectors which correspond to this eigenvalue. Okay.
So that's what we exactly get when we measure, and the psi is what we will measure if we have all eigenvalues in it.
Yep, exactly. Yep. So and as another, actually, so if all our projectors, what is called is of rank 1, yes, it means again that all eigenvalues are different. Then we have this. So we do not need this normalization condition in the bottom. So we obtain this psi I, as usually people say. Okay. So I think. And let me just look what I need to discuss here. Okay, and another just standard thing, but we need to say it. So so now we understand how to obtain. So what to obtain is a measurement, and for example, we can think about mean value of our observable. Okay, and so mean value, what does it mean? That I consider all the values which I obtain in my experiment times the probabilities that I really obtain this value. Okay, and from Born rule, what do we have? So we have the summation. Here I have this lambda I, and the probability is given by this psi times pi times psi. Okay, and you see that actually we can take this psi i's, move it from our sum, and then in the middle of our sum we obtain just so let me write it. So we have this psi. Here we have the summation lambda I times pi I with tilde. Okay, this psi, and you see this is just our operator, and we come to this standard expression psi O psi. Okay, so what you know from basic quantum mechanics. Okay, okay, but in quantum information, it's really important. Not the mean values, but it's really important these probabilities to obtain different outcomes. Okay, so any questions so far?
Just clarify about the probability operator. It's maybe I'm a bit retarded, but let's go up a bit. And you have two relations for PR lambda I.
one with tilt and one without.
Sorry.
What's intended is like here you have tilt, and on the previous slide, no, let's go even further back.
Yep.
Yeah, like here you have the same thing written for lambda I without tilt.
Actually, that is why so here is let's say, so what I considered here is a case where
Some of the eyes are equal, yeah?
yes, where this all the lambda i's are different.
But,
Okay, yeah.
So actually, yes, you need to have this lambda I tilt. Anyway.
We get that each, for example, I have each lambda I, and eigenspace of lambda I has dimension 1. Yeah.
Yeah.
So if you say that some psi i's have the same lambda i's,
yep.
so then this psi i's is just constant times other psi. For example, you write there psi 0, and psi 1, and the difference between them must be just a constant. No? If two different eigenvectors correspond to one eigenvalue, then they differ only to constant.
Nope.
No.
So, for example, let me.
Because we said that we diagonalized our Hamiltonian, yeah.
Okay.
So just eigenspace of each lambda i's is just 1. No.
Okay. Let us maybe consider the example. Let me consider the example the following way. So O, let's say it has the following form. It's 1, 1, 2. Okay. And here I have zeros. And let us consider a state like, I do not know, alpha, beta, gamma. Okay. And let us think about what will happen if I put this state psi into the, if I measure this state psi with this observable O. So let us think what I will obtain. So again, I have my observable in this form. So no. So I would like to obtain the whole picture with all the different possibilities of outcomes, their probabilities, and so on.
So you will obtain 1 with probability alpha squared with beta squared.
Yep, exactly. So so what I can obtain first, I obtain my eigenvalues. So the matrix is already diagonalized. So I have my eigenvalues already on diagonal. Okay. So you see that actually what I can say. I can say that lambda 1 is equal to 1, lambda 2 is equal to 1, lambda 3 is equal to 2. But what I would like to have all distinct. So I say lambda 1 with tilt equal to 1, lambda 2 with tilt equal to 2. Okay, and for this eigenvalue, I have a number. Actually, what is the eigenvalues for eigenvectors for this eigenvalue? First of all, I can say, okay, it's like this. But however, the things like, I don't know, like cosine phi sine phi and minus sine phi cosine phi are also good eigenvalues. They are orthogonal to each other, and so actually any kind of you know. So here we have some subspace which is spanned by these two vectors, and I can choose a number of different bases in this subspace. Okay, and this is just a kind of them. Okay, and for the second eigenvalue, I have this only so my eigenvector has this form. Okay, okay. Then so what I obtain a value +1 with a probability actually is given by psi. Let's say 1, 1, 0, which is a projector. Yes. So this is a projector spanned by these two, by these guys or these guys, whatever. Okay. And it's really gives me alpha squared plus beta squared. Okay. And here, and with probability, and also I can obtain the second value too, again with probability gamma squared. So it's clear. Okay. And what is, let us think, what are the final states which I obtain? So in the first case, if I measure my state and obtain on a screen of my observer, of my device, I obtain +1, what I will obtain?
Beta 0.
So what I obtain, so I should to act with a projector on my space. So what I obtain something like alpha beta 0. And then I need to this normalization factor, which will be alpha squared plus beta squared, something like this, yes. And in this case, if I obtain 2, what I obtain here is just 0, 0, 1. So it's clear now, okay?
Можете еще раз вот эта волновая функция с волной, это типа состояние, которое мы получаем после измерения? Вот это что?
Yep. So it's my what is called as yes, as post measurement state or post. Sometimes there is some conception what's called post selection. It's so it's a story when I make some measurement and then I discard some outcomes which I do not desire. For example, so I make measurement. Look what was the result of my measurement. And if it's, for example, +1, I say, okay, I will work with this state next. And if it's equal to +2, I just threw it away. And then I can consider all these cases where I obtain these +1s and the description of these states when I obtain this +1 is given by this. So this is my post-selected state. Okay, so any other questions? Okay, and here let me, so this is my prepared example. Let me just copy paste it from the original version of lectures. Let me put it here. So this was an example on again on a on a qubit story. So when we work with qubits, there are this very basic concept of Pauli matrices, and here they are. So here you see three matrices. For some reasons, they called sigma y, sigma x, sigma y, sigma z. So they have the following form, and you see that actually they are Hermitian, so it's okay. And so this is the form of, they are considered in the form of matrices. And next, so here I write what is called spectral decomposition of this matrices, and you see that all these matrices have these eigenvalues equal to +1 and -1, +1 and -1. Okay. And the eigenvectors have the following form. So for sigma z, the eigenvalues of sigma z are just my computational basis states. That is why it's diagonal. And for sigma x, I have this also very common state, which is denoted by plus or minus. So the plus state is given by 0 + 1, yes, divided by square 1 by square root of 2. And for -1 and for state minus, so we have this minus here, okay. And you see that they are orthogonal to each other, yes. And for the sigma y, the most, let's say, non-convenient operator, we have these eigenvalues, eigenvectors, which usually denoted by R and L. So this notation actually comes from optics. So they correspond to right-hand polarized and left-hand polarized light. And you see that so they have this imaginary I, and again this plus I or minus I. Okay, and so the most important is the position of these vectors in the block sphere. So you see that so for example the eigenvectors of the sigma z operators, so actually they correspond to the z-axis. So this is 0, this is 1. Okay, the same story is about eigenvalues of sigma x. This is plus and minus, so you see that they are along the x-axis. And the same story about L and L, R and L, so they correspond to y-axis. Okay, actually, this is why this matrix is sigma I, sigma X, sigma Z have this X and Y and Z. Okay, in the subindex. Okay, and again, important point here is that orthogonal states in the block space representation, they are not orthogonal. Yes, you see that they are opposite. Sometimes it leads to some misleading. So there are some misleadings. So here should be important. Well, so any questions about this stuff? So it's quite common. Okay, and here I consider some illustrative example. Again, I choose the state psi, which has this form. So let me ask. So what do you think? Where is this state psi is in the block space? How it looks like? Somewhere between R and 0. Okay. Why? Yes. Actually, it's in the ZX plane. Yes, somewhere in this XZ plane. So maybe somewhere like here, for example. Yes. Here is this angle theta. So it's somewhere in this plane. Okay, and for example, I would like to measure the sigma x observable. Okay, and what I obtain? So I obtain, as we remember, so sigma x has this, so it has this form plus plus minus minus minus. So we obtain either +1 or -1, and we obtain +1 with this probability. So again, so here is this overlap between my eigenvector because it's single. So all these projectors are of rank 1, and so they are given by this expression. So it's, you can easily check this. And if you measure the eigenvalue, oh sorry, the mean value of your sigma x, so you can just put it in this construction, and just make some calculations and finally come to this expression sin theta. And actually, you see that this sin theta corresponds to the projection of my block state on a x-axis. So because here is this theta, okay, and actually you can check that if you let's say if you take some state psi and you measure and you consider its mean values of these three operators, then these three mean values will give you actually a coordinates of your block vector yes, so they give the coordinates of your block vector. Okay, and actually in this self-check assignment, which you can see on a GitHub page, there is an exercise to check this. So this is true. Okay. So any questions so far? So does it clear? Okay. I hope this is very clear. Okay. So let us move. So please say me when we need a break. Yes, because as I remember, we have two lectures today. Yes. Okay. So the next important point, the next important topic is what is called the mixed state. Let me move it like here. So so this is the second, let's say the second type of states, which are very useful in quantum for description of states, and it has the following idea. So imagine you have what here I so some kind of buckets, okay, with particles, and imagine you have here m buckets, and in each bucket you have particles in some particular pure state. For example, in first bucket you have this psi1, some particles with the state psi1. Here we have some psi2. Here we have this psi m, and actually the product of this psi's can be arbitrary. So they are not orthogonal, just some states. Okay, and imagine that I take these particles with some probabilities from each bucket and put it into another bucket. Okay, just take and put. And so for example, I take P1 portion of first states, P2 portion of second states, PM of M states. So this is P is just this coefficients, which the sum of them equal to 1. So it's really a portion. Okay, and I just take the states and put it into one bucket. Okay, and give this bucket to some other person, and this person cannot distinguish them. So he just takes this particle at random, and let us think what will be the result of measurement which he obtain on this particle. Okay, and imagine I take some arbitrary operator O, whatever. Okay, and I take this random particle from this bucket, the resulting bucket, and just look what will happen. And the idea is the following. So let my operator O has some spectral decomposition, and inside the spectral decomposition there is a term with some lambda. So remember, lambda is some real value which corresponds to what he will see on his screen, and P is some projector. So I do not put this I subindex to, because there will be other subindices. Just okay. So just some of the projection, and let us see what will be the probability to obtain this value lambda. Okay, or if I take the state from this bucket, and so what we know that so this is the general rule. So this is a board rule for our measurement outcome. Okay, but so what I know, so I know that with probability pi, I will have this state psi I. Yes, and this is why this this probability has this form. Okay, so I need to calculate a mean value with respect to all the components, all these components. Okay, and so I have this, so it's given by this way. And then I use the following rule that if I have some, let's say, operator M, and I have this M psi M psi, and this actually equal to trace over M times psi. So you can just check that it's really so. Okay, and I use this trick, yes, and rewrite it in the following way. Yes. So I put this psi i's and pi's. So I write it in this way. Okay, and then I put this pi's inside, and actually I come to this construction. So I have this my projector P times this construction with this pi times psi I, and actually you see that I obtain some this construction, and this construction actually describes the whole ensemble. Yes, so I have this convenient form. Yes, and actually this construction is what is called a density matrix. Yes, and so I can write the result in this compact form, that I have my projector times this operator, which describes me the whole state which I obtain in my final bucket. Okay, and well, it's called a density matrix. And people say that in this case we work with what is called a mixed state. Yes. Well, so any questions?
There's no indexing by I. Yeah?
Actually, yes. So because so actually you can think like this. So I can put some, let's say, by j, yes, because there is my operator O, of course, is like lambda 1 pi 1 plus lambda 2 pi 2 plus blah 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 blah. Okay, and I just take one of them and do not without index, but actually there should be an index. So it's just so okay. So you can think like I have lambda j.
Oh, okay.
Yes.
Yeah.
This is j. This is j here, and so on. And however, so there is no pi I here, of course. So questions?
Вот можно объяснить вот этот переход, вот у вас квадратный может быть на формулу, и вот к трейсу переход.
Okay, so again, so let me maybe more. So there is this, the trick is the following. So I have this psi times pi times psi. That's here I have some I, and here let's say j, okay? And I say that the following is true, that it's equal to pi j times psi I times psi I. Why it is true? Okay, let me explain. The way how you can think is the following. So here is a trace operator. So what is trace? Trace is a sum of all diagonal elements. But trace, as we'll discuss a bit further, have the following property. The trace is independent from the basis you choose. Okay? And you can think, okay, let me compute my trace with respect to a basis where this basis is constructed up on psi I. So I take psi I, and then I put some other vectors which gives me let's say, I do not know, like k. Oh no, so like I1 like I1 psi I2 blah blah blah. Yes, and let be my orthonormal basis, okay, where I have this psi I, and let me compute this trace with respect to this basis. Okay, what will be this trace? It will be like psi I times this construction. So it's the first diagonal element, okay, plus psi I1 times this construction. Yep. Plus so on. And then I see the following trick. So this is orthonormal basis, okay? And here I have this, So here I have this kind of terms. And you see that they all will die. And only the first term will survive. Okay? And this is why this is true. And this is what we use. So we use this so we put this so we use trace, yes, in this construction. And then so it's just then we put this this summation. So again, trace is linear operator, so we can put our summation inside trace. And here we come to this construction of our density matrix. Okay. So questions? Other something? So clear. Nice. Well, So what is so one statement which I also copy paste from my original version is the following: that actually what is important, and sometimes it also leads to some misleadings, is the following: that remember that here my psi i's, which I used in order to construct my state, they can be arbitrary. That can be the same, they can be different, they have different overlaps and so on. Meanwhile, each of my states has its own spectral decomposition. So for any density matrix row, okay, so for any density matrix row, I can represent it in diagonal form, and for each density matrix row, I have some d components, d eigenvectors psi I with tilde, yes, with some probabilities pi with tilde, and they can be different, of course, from this pi's and psi's, from a source of my mixed state. Okay, but nevertheless, so I can always obtain them. Okay, but importantly that this new psi's, they of course are orthogonal to each other because it's my spectral decomposition. Okay, And so there are some PIs with tilt, so they also like a probability distribution, so they are non-negative and gives 1 in sum. Okay, and this density matrices, so they have some standard, also quite well-known properties. So let us just discuss them a bit. So the first property, of course, you see that the density matrices are Hermitian, just because from the construction, because they are constructed in this form. Yes, so we have this psi I times psi I, and so they give us Hermitian matrix. So the second property is, of course, that trace of my density matrix is equal to 1. It just comes from this, just also from the construction, because the probabilities, so the sum of all probabilities, which I take my states from buckets, they equal to 1. Well, the third property, yes, so it's called, so people say that density matrices like positive semi-definite, and it's just another way to say they are non-negative. So what does it mean, non-negative? So the idea is the following: that if I take arbitrary state psi, okay, and I obtain this form of, so I consider this kind of product, psi rho psi, then I should obtain some number which is greater than 0. Okay, and so actually, so this is again, so it follows from the construction, and its core, this property has the fact that these probabilities with which I take my states, they are non-negative. Okay. Well, so this is the third property, and so the fourth property is that if I consider that trace not of the state by its squared, so here I have this rho squared, okay, so then this trace is less or equal than 1, okay, and actually the only way how I can obtain a trace of my density matrix equal to 1 is that my state is pure. So from this point of view, the pure state means that actually like I have only one bucket, and I always take my state from this bucket, and I do not use any other buckets. Okay, and in this case, I obtain really my pure state, and the trace of rho squared is equal to 1, and actually this value, trace of rho squared, it's quite common and quite convenient way to measure mixedness. So it's how to describe how at which extent your state is mixed. Okay, and this quantity. So you see that if I use the trace rho squared, so if my state is pure, then I have 1. If I have a mixed state, I have some lower variables than 1. And sometimes it's more common to use this construction, is 1 minus trace rho squared, just to make that the more this value, the more the state is mixed. And sometimes it's called what is called linear entropy. Yes, babe. So here is the following intuition, that the entropy, as we will see, it's kind of a measure of chaoticness. So, and the mixedness here is kind of equivalence of this chaoticness. So if your state is pure, it's definite, because you always can construct an observable which consists of projectors only of rank 1, and you can construct such observable that this observable always will give you the same outcome for the state. So it's equal for pure states, and it's larger than it's equal to 0 for pure states, and it's larger than 0 for mixed states, and this is the property of entropy.
Does this definition correspond to any others, from statistical physics or any
Или
else?
там Шеннон, метрика.
Actually, no.
How does
So it's very useful because it has very useful. It's very simple construction because we have this rho squared. You check just rho times rho, and for example, if you consider this for name and entropy, you have this rho logarithm rho, and this logarithm is terrible. And this is how you can easily calculate things. Okay. Yes. Well, and the last very important property is that actually each of mixed states have it can be decomposed in different forms. So each mixed states can be constructed from, let's say, different ensembles. So for example, you can choose one set of pi's and psi's. You can take another set of pi's and psi's and so on. And we will see it in an example. So maybe one of the most common examples of mixed states is what is called maximally mixed state. Let me put it here. Example. So the maximally mixed state is just so it's a state with a matrix which is proportional to diagonal. So because of so we need to have this trace equal to 1. This is why we have this 1 over d, where d is the dimension of my space on diagonal. Okay. And so in the case of d equal to 2, we have, of course, this form of this matrix, and this matrix can be combined in different ways. So for example, I can think about my mixed states as I have some zeros and ones, and I take with a probability 1/2 I state 0, and with probability with 1/2 I obtain a state 1. Okay, and in the same way I can look at in this form. So I take with the probability 1/2 and I take some state plus, and with probability 1/2 I take the state minus. Okay, and it will also give me the same matrix. Or in the same way, I consider it in the following form. Okay, so this probability 1/4 I take 0, so probability 1/4 ones, 1/4 plus, and 1/4 minus, and so they can be a lot of them. And actually, you can check that there is an infinite number of decompositions of mixed states. Okay. Well, and so the final thing, I think. So let me also put it. So actually, if we speak about density, again about qubit density matrices, mixed states of qubits. So each of the density matrices for qubits can be decomposed in this nice form. So you see that here, so it have 4 terms. So the first term is identical matrix times 2 divided by 2. So this matrix actually gives me this trace equal to 1. Okay, and then I have these 3 terms: x sigma x, y sigma y, z sigma z. Where this x, y, and z are some real parameters. Okay, and it also will be from your self-check assignment to check that these real values should satisfy this constraint, which actually corresponds to a sphere. Okay, and this equality to 1 corresponds to pure states. Okay, and so this is an example of state. So this is my block vector. So the maximally mixed state corresponds to a center of my block sphere, because so if I choose x, y, and z here to be equal to 0, you see that I obtain the only identity matrix. And for example, this state is this form. For example, it corresponds somewhere here. Okay, on the explain. Okay. So, any questions so far? So there is silence in the audience. Okay, I hope that everything is correct. Everything is quite understandable. So, okay, so I decide maybe to have some break, small break. And meanwhile, so the question for the audience is the following, for just to understand that all we understand. The question is the following. So consider state psi like this, 0 and 1. Okay, is the first. And next, consider the maximally mixed state, 1/2, 1/2. So my question is how to distinguish the states. So for example, someone comes to you and gives you a state, either this one or this one. And the question for you, just to think a bit, how to distinguish them. So they do not give you a matrix. They give you a particle. And you have
measure it and get the state.
So I encourage you, each of you, just not to pronounce an answer, just to think what thing I should measure, what kinds of measurements I should use in order to distinguish between these two states. So let's have a small break. I think let's end 11:15. Okay. Пом-пом-пом-пом. Так, что надо нажать? Нажать Zoom. Well, so it's quite easy, but it's really important to understand this stuff. Okay, so let me remind the question. The question was the following. So consider I have a source which gives me either pure states which described with this psi vector, or this source gives me a density matrix in this form. So it gives him a maximally mixed density matrix. And the question was how to distinguish, how to understand what kind of source is this source. Okay. And so the first thing which I think I need to mention is the following. So we see that in the first case I have some pure state which is described by a vector. In the second case I have this density matrix which is actually an operator which acts in my state space. So and it looks like that these are two kinds of objects from different universes. However, it is not the case. So for the first point is that for each pure state, we can think about this pure state as a density matrix. And the density matrix for pure state is given by this expression. Okay? And if we write explicitly the density matrix of the density matrix, we obtain to this form. Okay? So I hope that is clear. And you see that this density matrix and this density matrix, they are not the same. Okay? Because of these non-diagonal elements, which actually are very important. However, non-diagonal elements are the same. And the question was, okay, so by the way, so how to distinguish? How to distinguish these two cases? Okay, and so any okay, so any ideas? Maybe other ideas. So there was one idea by Alena, maybe some others. So
the first idea was just to measure the probabilities of zeros and ones for each state, but this way we can distinguish.
Okay.
So Alena said like there is like sigma plus operator or sigma x, yeah, operator.
Yeah.
Yeah.
So we relate
What if we change
trace
buttons?
raw sigma x, yeah.
Yes. So actually, how can we think about it? So the easiest way how to think is the following. So let us go back to our block vector. Okay. So and remember where is so where is this x, y, z? Okay. And where is my states are? So where is my mixed state? In the center, yes. So this is my row, okay, and my psi, where it is? Yes, more concretely.
It's just sigma plus. Oh, it's just plus.
It's just plus. So where is plus? On the x-ray. Okay, it's here. Okay, and so this is my psi. And the question is, okay, how to distinguish this psi, so the point. So this point and that point. Okay. Yes, and so the answer is yes, of course. So I can just measure the projection of this state on the x plane, on the x-axis, and if it is equal to 1, yes, so then I have this. I have state psi, and if it is equal to 0, then it's equal. So then it's then I have mixed state. So more, let's say concretely, the situation is the following. So if we take my sigma x, if we take the sigma x observable, okay. So if I put inside my state psi, what I will obtain? So remember, I obtain +1 with probability 1. Yes, always. So with probability 1, I always obtain +1. Okay, and if I take my row, yes, and measure sigma x, what I will obtain?
I think
So each time, so I take my particle, put it into this measurement apparatus, and what I will obtain?
You play the coin toss.
Yep. So what does it mean? So what I will see on the screen?
50 zeros. Oh,
yeah.
Minus 1 and 1.
Yeah. So with the probability 1/2, yes, I will obtain +1. Okay. Okay. So with the probability 1/2, I will obtain +1, and with probability 1/2, I will obtain -1. Okay. And the way, so you see that if I take my particle, and put it into my measurement operators, so if I obtain +1, so actually it does not say me nothing, because it can be either from psi or from rho. But if I obtain -1, I'm sure that really I have this rho, but not my state psi. And again, the way how you can think about it is the following: that if you consider your state rho, then you can decompose it in a way like this: plus 1/2 minus. So inside your state maximally mixed state rho, you have half of the particles in the same state plus, which just equal to psi, okay, and half of the particles in some orthogonal state, okay. In a zero, in what sense? So okay, why? So the idea is the following: that your coordinate of your state corresponds to a mean values of the sigma x, sigma y, sigma z operators, and you can think the following: that your maximally mixed state is a quite it's fully random state. So it's like a spin 100 particle, which is fully random. And if you will try to measure any projection of your chaotic state, as a mean value, you will obtain 0, because it's fully chaotic. There is no any anisotropy. Okay, and this is why you have this 0. Okay. So any other questions? No questions. Okay. Well, so let us move next, and then we come to the next topic. So we go to what is called bipartite systems. Okay, it's yep.
элементы, но там они с разными весами, там c и c минус 1.
Okay.
Вот что там будет,
So the question for the audience. So,
Ответ будет смещена, скорее всего, да?
how, so yes. So the question is the following.
Ну, если
So,
у нас смешное состояние.
I have some density matrix row, okay? And it has this form. So what is where the states is in the block, on the block space, on this block sphere.
I think we should calculate.
Calculate.
XY, etc.
Okay. Calculate. Okay. So no intuition. Oh, okay. So let's move. So I have this diagonal form.
Ну, надо выбрать C, что это разве вот так он работает?
Okay, so let us. Okay. So let us. Just okay. Let's think the following. So. Actually, I think so. If C is equal to 1, where?
What?
If C equal to 1, we are here. Yep. Yes. If C equal to 0,
We're down.
we are here. If C equal to 1/2, in the middle. Yes. So what does it mean? So we're somewhere. So if we move our C from 1 to 0, we move from the north pole to the south pole.
So, yes, the decomposition you wrote before,
yep.
It's like 1/2, 0, 0, 1/2 plus C minus 1/2
yep.
times sigma z.
Yep.
So the coordinate in sigma z is
yes. So it's 1/2 like this. Yes. Plus, and here I have 1/2. Here I have this 1 minus 1, and here I should reconstruct something in order to obtain this form. So what I should, so it's like 1/2 plus 1/2 z is equal to C, yes? And from this I get this C, I have this, okay, I have this z equal to C minus 1/2 times 2.
Yeah, in factor is C minus 1.
Z is equal, yep, so this is how it works. So it's actually Z is equal to 2C minus 1. Okay, so it's if C is equal to 1, I have this 1. Okay, this is. So, and here is this Z. Okay. So something to, so clear, yeah. So it depends on which kind of phase do you mean? Where is phi? Yes, so it's a question. Okay, so nevertheless, so okay, so this is how it works. Okay. So any other questions? Okay. Well, something is not clear.
Да, вот вы там написали про Z, но мы помним там X, Y.
So you can check that they will equal to 0. Okay. So there is no projections. Okay. So you see that this sigma x actually corresponds to a real part of your non-diagonal elements of your density matrix, and sigma y corresponds to imaginary part of your non-diagonal elements. You can think like this. Okay. So the next topic is what I call bipartite systems. So it means like a system which consists of two parts, of let's say two particles. And we already know that if I have, let's say, one particle, I have some Hilbert space. In this Hilbert space, I have some basis, and so on. So here is a story about two particles. And let these two particles be described by two Hilbert spaces, some HA and HB. They can have different dimensionalities. Okay, and in the space of each particle, I can define some basis. Here I denoted with EI and HI. Yes, where I goes from 1 to dA and to dB, where this dA and dB are dimensions. Okay, and the axiomatics of the quantum mechanics says that, okay, if I would like to describe the whole state of this combined of this these two particles, I need to introduce the joint like a joint Hilbert space, which corresponds to what is called tensor product. So I need to construct a tensor product of my two Hilbert spaces. And so what is a tensor product? It's a new space so it's Hilbert space, okay? And this space have some basis, okay? And this basis is constructed from the basis vectors of these two spaces with what is called a tensor product operation. Yes, and you see that the number of this set is given by dA times dB. So for each pair, for each vector from the first space and each vector from the second space, I can construct a new basis vector from the new vector for a new space. Okay, and the idea is that this vectors corresponds to orthonormal basis. It means that if I consider sorry, there is a misprint here, because here I should have this H. Okay, so if I have two vectors, yes, each vector described with different indices I and j, and here is this k and l, and I multiply it by each other, what I obtain. So I can think that in the first space I have this tensor product of this EI and EK. In the second space I have this tensor product of this H's. Yes, and the whole product is given by a product, by a traditional scalar product of these states in each of spaces. And what I obtain these Kronecker symbols. And you see that the only way how these vectors will give me a unit product is where I equal to k and k equal to l. Okay, so this indices which corresponds to each of subspaces are equal. So it's a general rule. Okay, so let me remove this. Okay, then what next? So if I consider a state of my system in this new space, I can decompose it with respect to a new basis, and so this is so the pure state has the standard form of decomposition. So you see that here is this coefficient of my decomposition. They already have two indices I and j, which corresponds to different spaces. The A, or the space of A and the space of B. Okay, and so the normalization condition on this coefficients is the same. So the sum of amplitude squares is equal to 1. And the only point which I would like to note that actually, so people use different notations very often, and they can be like this one. So we take a vector from the first space, we take a vector from the second space, and we emphasize that we work in the particular space of the first system and in the space of the second system by these subindices. Okay, sometimes people do not use this. Yes, do not use the subindices and write just like this. Okay, sometimes people put this tensor product, sometimes people do not put this tensor product. It's also okay. And sometimes they put these two labels of vectors in a single cat, or like they put it like this. So there are a bunch of different ways how people denote the things, but usually you understand what people would like to say. So it's okay. Well, so actually there are two ways how you can think about tensor product, and how can you think about, let's say, a pure state of your composite system. And the first way, which we will not, maybe we will discuss it in our final part of our lecture course, is what actually Ilya Lushnikov told us in the last lecture, in the final lecture of the school, is what is called tensor networks and tensors. So so the first way how you can think about this set of coefficients, you can actually think about it as a tensor. Yes. So it's some mathematical concept, some mathematical abstraction, some object which have some two indices, and which these indices you can put in this some let's say integer numbers, some indices. So you have some object with two indices, and for each pair of indices you obtain some complex value. So this is a standard way. It's tensor. Yes. And the second way how you can think about it, you can think about your let's say your state of your composite system also as a huge vector. Yes. So the idea is, so you have these two spaces, you have vectors which correspond to these two spaces, and you can construct a huge vector which corresponds to a state of your composite system. And so, for example, if you have this some basis a basis vector in your first space, okay, so you have some EI which has this unit element on some i's position, and this is this vector of dimension dA, and you have this vector of dimension dB with some element on the position j, and then you can use what is called a tensor product, or sometimes it's called Kronecker product, with the following rule. Okay, so you take your first vector and you like put your second vector near all the elements of your first vector, like this. Yes, and then you multiply all these elements, and you obtain the whole large vector. And actually, for the case of the basis vector, you also will obtain a huge vector with only one unit element, with this position which is described by indices I and j. Okay, so this is just a standard rule of Kronecker product. Okay, and the same very similar story is about operators. So if we have some operators which are defined in each of the spaces, okay, so you have this like A and B operators, and we have some. So for each operator, we can think about each operator as this kind of construction. So this is all of my elements. Yes, and this is my matrix, which has some unit element on the I and j position. Okay, and all other are zeros, and I can decompose my matrix. Okay, and so, and if I have these two matrices, then I can what I can make a tensor product of them by the following rule. So I have this huge construction. Oops, sorry. I have this huge construction like this. Okay, and the idea is the following: that if I take a tensor product of my operators, yes, and this tensor product of operators acts on some tensor product of states, then what I obtain a tensor product of, let's say, the first operator, the result of the first operator acting on the first vector, the second operator on the second vector, and just tensor product of them. That you see, that's quite intuitive. Yeah. And if we consider the construction of this composite operator, yes, so we can consider it in the following form. So we just take this decomposition. Yes. So this kind of explicit decompositions, put it inside this tensor product expression. I don't know if I should use it. And what I obtain the whole in matrix. Yes. So you see that the idea is quite the same. Yes, that I take the elements of my first operator, and each element of my first operator I just multiply it by the second operator. Yes, and I obtain again a huge matrix. So actually, its dimension will be given by dA times dB. Yes, and this is also dA times dB. Okay. And this construction acts on my state. Okay. Well, any questions so far? No question. Okay. So the Kronecker product, the idea is the following. So imagine I have this like a vector A times B, AB, Kronecker CD. What I should do? I should take my second vector and put it inside the first vector. And then I will obtain something like this. So I obtain A times CD. And here I have B times CD, okay? And then I open the brackets, let's say, and I have obtained AC, AD, BC, BD. Okay. And actually, I have an example. Let us consider an example for a qubit case, which is the most important for us, as usual. So again, we have this 2 by 2. We have this case of dimension equal to 2. As usual, the basis vectors are denoted zeros and ones. Okay, and for example, I take this sigma x and sigma z matrices. Okay, and then we can consider all the basis, let's say the basis states of my tensor product state. And for example, 0, 0, which corresponds to this one. Okay, and how I compute it? Again, I take my first vector multiplied by the second vector. Here I need, okay, like this, yes, and I obtain this vector. Okay. And the same story about all other vectors. For example, I do not know, like, okay, like 0, 1. Okay, I have 0, I have 1, and I multiply it and I play like this: 1, 0, and 1, 1. And you see that there is the position of this unit element is not random. So you see that it moves. So if I consider all these different basis vectors, you see that the identity element, the unit element moves from the top to the bottom. Yes, and actually there is quite useful intuition or trick is the following, that we can consider let's say counting in a binary representation. So usually we use this decimal representation: 0, 1, 2, 3, 4, 5, 6, 7, so on. And we can consider also, we can count this binary representation, and then the sequence of bits will be the following. Yes, so it's 0, 0, then 0, 1, then 1, 0, then 1, 1, and so on. Okay, and you see that actually the position of this identity of this unit element, yes, so this one, actually you can obtain it from considering this label as an integer. Yes, for example, 0, 1, from the point of binary representation, it corresponds to 2. Yes, and so the only moment that you should remember that in order to use these tricks, you should think about counting it like in a Python style. Yes, so the first element is the element with a number 0. Yes, with the index 0. So you count 0, 1, 2, 3, and so on. Yes, like this elements in Python arrays and so on. And if so you can easily obtain the position of this unit element in your composite composite space. Okay. So any questions about this stuff? So I hope that is quite clear. Okay. Well, and here an example. So this is what is called a Bell state. Next we will denote it with phi plus, but now it's just some random state. So here we have this 0, 0, and 1, 1, and one can see that this state corresponds to this vector. Okay, So because if the first one corresponds to this vector, yes, and the second one corresponds to like this vector. Okay, and I put it like this. And also another example, I can consider tensor product of my operators. For example, I can consider this sigma z times sigma x, and the idea is the same. I take my second operator, put it inside the first operator, yes, and what you see is that here I have this my sigma x, and here I have this minus sigma x because of this minus one here. Okay, it's also quite trivial. Well, so that's it, I think. So maybe some more questions, or so it's clear. Okay. Well, then we come to the next topic. It actually it's also very, I think it's quite easy, quite simple. But however, so I remember myself when I first studied this stuff, and it was not so simple for me at first glance. So it was kind of magic. And I spent some time to understand that there is no magic. It's quite simple. So I will try to describe it in such a way that I hope you will understand. So this is a story about what is called partial trace. And before we start speaking about partial trace, let us speak a bit about simple trace, not partial, but let's say complete or full trace. Okay, and the story is the following. So imagine we have some Hilbert space, okay? We have with some dimension, with some orthonormal basis, and here I to denote my basis states, I will just use this with y1, just a label 0, 1, 2, 3 up to d minus 1, where d is my dimension, okay? And I have some operator, some metrics, okay? With elements given by which I can obtain by this expression, and the trace, as you remember again, so trace is just the sum of all diagonal elements, and we can think about diagonal elements in the following form. So I take my metrics and multiply it by these two i's, bra I and cat I, okay, and so in this way I obtain my diagonal element. And so the trace have some two. Here I noted two properties. So the first property is that properties. So okay. So the first property is that trace for a multiple AB is equal to trace of BA. Yes, however, so it's always the case. However, so as you know, in a non-commute, so A and B could not commute, and in general case, AB is not equal to BA. However, their traces are equal. And the important points, sometimes people miss it. So, so in concert, so okay, we have this property, but we do not have this property. So you see that if I have the product of three matrices, like A, B, and C, it is not equal to A, C, and B. Because you see that here I swapped these two matrices, and it is not the same as the story about swapping A and B and B and B. Yep, exactly. So but however, what I can write, I can write like CAB. So this is true, yes, because I move C. So I cyclically, yes, I moved it. Yes. I'm not sure how you can define trace operator for a non-diagonal matrix. Honestly, maybe. Honestly, I do not know. I do not ever think about it. So let it be my homework exercise. I don't know. So maybe. So, but in usual, so usually, so in our science, we work with squared metrics. Nope. So here I have my no tensor products at this point. So just simple multiplication. Yep. So it will be the next time to this the next point to discuss. Okay. And another important moment is that trace operator is invariant under the change of basis. So if I have two bases, here I have my i's and here I have my ei's, where this ei is just some other orthonormal basis, then actually, so the trace is invariant. Yes. So the trace is not a property of your, let's say, matrix representation, but it's a property of your operator. So it is independent from the representation of your matrix in some particular basis. And the easy way how you can feel why it is so is the following: that, so for example, if you consider your operator A, okay, and if you change the basis representation of your matrix, you can think about it as applying some unitary operators. We'll speak about unitary operators in the next topic. So you can just put your unitary operators, and then because of this trace, because of this this rule, you can move your unitary operator from the last position to the first position, and you just obtain this u plus times u, and this is identical operation. So finally, you obtain the same. Okay. Well, so that's it about some simple trace operator, and then let us think about the case where we have our bipartite system. Okay, where I have these two spaces. Okay, so let me have the first, let's say, the first state HA, the first space HA with some dimension dA, and with some orthonormal basis inside the space. Okay, and the second, the same is for the space HB. Yes. So yes, here I just should remove this B. Okay. Oh, sorry. Oh, so it's okay. Yes, of course. So you can change index as you want. Okay, and so you can consider the tensor product. Yes. So tensor product of the states. So again, the dimension of your tensor product will give us the new space, which is given by a product of this dA times dB. Okay, and so we have this new orthonormal basis obtained from the tensor product of states. Okay, and next I can consider some operator. For example, here I choose operator M in this composite space of HB of A and B, and you see that because I have these two spaces, it's like decomposition in this basis. It's have a more that's more sophisticated form. You see that here I have so I have already 4 indices, because I have an index which corresponds to a basis, let's say in a first space in A system, in the space of A system, and in the space of B system. So I have this M, I, J, K, L. Yes, again. Oh, sorry. Okay. And again, remember that if I consider a standard product of two basis vectors, so here X is either A or B, then I obtain delta Kronecker symbol. Okay, and what I can do here, I can consider first a trace operator. So if I consider a trace of my matrix M in this composite composite space, so my trace operator will have the following form. So look, so again, so in order to consider a trace, so I need to put my matrix M into this bra and cat, yes, of all basis states, and all basis states have this form, this AI IA times JB, and here of course this is a tensor product between them, like this. Okay, and if I consider this, so the operation, so I should make the summation. So the summation over all diagonal elements will have this form where like I have two summations, okay, which corresponds to each of the spaces, and finally I obtain some value which is complex in general case. Okay, and this is a trace, the full trace. And then we come to a concept what is called a partial trace, and the partial trace corresponds to the fact that so in this summation I remove, let's say, terms which corresponds to the basis in in one of two spaces. And here is here is a here is an expression. So the and here, so what I have. So here I say, okay, let me compute my trace with respect only to the basis in the space A. Yes, and so I take my operator M and put it in this what is called sometimes sandwich of this cat and bra from A subsystem. So this index I goes from 0 to the dA minus 1. Well, and actually there is some tricky point. Tricky point is the following, that this for example this vector IA, actually it's a vector which is of dimension dA. Yes, so it has some unit and has some zeros. Okay, and here this matrix M is a dA times dB. Yes, some matrix, some huge matrix. Okay, and then I multiply it here. I again multiply it by a vector of a dimension dA. And formally, this operation is not correct. Yes, because we cannot multiply a matrix. So the dimensions of my matrix does not correspond to the dimension of my vector. Yes, because so if I will just try to multiply it, I will fail. Yes, because so they are not the same. However, how you should think about this construction, you should move back to representation of your operator. You should move back to this. Let me maybe like just copy it from here. You should take this representation. Okay. So you should take this representation, and then it's become so if you take this representation, you can actually apply this form. So look, so you take this vectors EI, yes, and you multiply it, so they live in your A space, and you multiply it by M. So maybe it's not. So let me.
Is it correct? Because I guess you should write A times the product 1. No.
A.
EA.
Actually, yes. Yes. So it's another way how you can think about it. Yes. Yes. It's okay. Yes. Yes. It's another way how you can think about it. Yes. Exactly. So you can think about. So you can put it like identity operator.
And there will no problem with.
Yes. So it's another way. Yes. Yes. But okay. So it's really the way how you can think about it. Yes. So, but the problem is usually no one writes this one once. This identity operators. So usually people write it like this. Okay. and you should be prepared for this. Okay, and so if you multiply, so so what will happen? So let me put this ij, let's say ijkl with primes in order to ijkl, and if you multiply, what how you can work with it, you move. So you move this I here, and you move your I here. Okay, and what you will obtain is that in the space of the A system, you will obtain just a standard products. Okay, and in the space of B system, you will still have this projector. And finally, what you will came to is this form. So you see that oh, I'm sorry for this mess. Let me maybe write it once again. So how it works. So let me remove it and write it more explicitly. So I take my operator. Let me move it here. Okay, I take my operator, yes, and let me and multiply it by, let's say, sum over, let's say I use here some I prime, yes, and I multiply I prime A, and here I use I prime A. Okay, and here I can just take like brackets. So this is my partial trace over the A subsystem. Yes, and what I do, I take this this operator and see what will happen in my A subspace. I should multiply this by this. Okay, so I should multiply it on this I, and this operator in this vector, because it lives in my A subsystem, you know, in the space of A subsystem, I should multiply it by this J. So I should put it here. Okay, and what I obtain this, and here I have this ijkl. Okay, and what I obtain is summation over I prime ijkl, then this matrix element ijkl, and here I have this I prime times I in the A subsystem times J times I prime also in the A subsystem, and then I have this KL in the B subsystem. Okay, and you see that because it's orthonormal basis, so these guys will survive only in the case where I is equal to I and equal to J. Okay, and this is why what I will finally obtain, I will obtain this let's say IIKL, yes, and here is this KL in the B space, and here is summation over I, K, and L. Okay, so this is really probably not so evident, maybe tricky, but however, so how do you feel about this? Is it okay? It's okay, perfect. Well, so this is the idea of partial trace, and the partial trace is a basic operation which is used in order to obtain what is called the reduced states of your system. So for example, you have your density matrix which describes the whole system, and you would like to obtain like states of your A system and your B system separately. And in order to do it, you need to use this partial trace. And the idea is that in order to obtain the state of A system, you need to make a trace of the second system. So you make the summation over B system and obtain the state of your A system. And the same is here. So in order to obtain B system, you make this trace over A system. And the intuition why it is so is the following: that so So for me, it was helpful for me. I don't, maybe it will helpful for some of you. So remember the story about your classical probability theory. So imagine that you have some joint random state, just classical random state, and it's described by some probability distribution. And for example, you have two random variables A and B. This is capital A and capital B, and you can define your probability distribution for all different outcomes, which I denote with this small a and small b. Okay. And for example, you would like to obtain your what is called marginal distribution. So the probability distribution for a variable and for b variable. And what you should do, you make the summation over the other subsystem. For example, you need to, if you would like to have this probability for a, yes, you need this summation over b. Okay, and this is quite an analog for this story about partial traces actually. So it has the same intuition. So in order to obtain the state of your first system, you should make the summation over all degrees of freedom of your second subsystem. So it's quite the same. Okay. So it's clear. So. Okay. Well. So let us consider an example. I hope that it will help us.
We consider density matrix like joint distribution for bipartite system.
Yep. So you see that actually what is the difference between the classical let's say random variables and quantum systems? And one of the ways how you can think about it is the following: that so imagine, so in your classical probability theory, for example, if we think about discrete random variables, so our discrete random variable is described by some probability distribution, discrete probability distribution, and you can think about it as a vector, for example. Okay, so you have the vector of your probabilities which correspond to different outcomes, and so there is this, let's say, probabilities pi's, and you know that each probability is greater than 0, and the sum of your probabilities, summation over all I for all pi's, is equal to 1. Okay, it's simple. And in quantum mechanics, you can see the following story: that first we take this probability distribution and like put it on a diagonal. Yes, so we put it on diagonal. Meanwhile, we add something on or from in this off diagonal, and this is our, let's say, quantum features. Yes. So and they also these non-diagonal elements. So you see that if you consider your measurement in your computational basis means that the basis which is used in order to write this matrix. So you see that if you use this computational basis measurement, you will exactly obtain this probability distribution. Okay. However, quantum mechanics say, look, so this is your measurement, but however, there are other measurements. And they will give you some more information, and other measurements actually will give you something which is hidden in this off diagonal part of your density matrix. This is how you can think about it. So this is a story about the difference between what we discussed, this psi, which is this plus measurement and plus state, and this diagonal matrix. Okay, so from the computational basis, it's just the same. Yes, because you have this the same elements on the diagonal. Yes, but however, quantum mechanics say, look, there is some more sophisticated stuff on non-diagonal, which you can obtain in other measurement, for example, in sigma x measurement in our case. Okay. So in some sense, this density matrices is a generalization of your classical probability distributions. And also, for example, in quantum cryptography, you will see that people often use quantum mechanics. So they use these formulas of density matrices in order to describe quite classical things, like what button Alice and Bob push. They also describe it with these cats and brass, and it's okay. So the density matrix is more complex, or more general way to think about probability. Well, so let us move back to our practical stuff. Up. Come on. So this is my example. The example is the following: that I consider some state. This is the pure state of bipartite system. I choose it in this form. So here is the square root. Square root should be, of course, like this. Okay, and so it's a state, yes. And what I can consider its density matrix. In order to consider density matrix, I should consider this product, of course. And finally, so I honestly calculate this product and obtain a matrix like this. Okay, again, this purity gives me this all non-diagonal elements, which comes from these cross products from, for example, 1, 1 and 0, 0, 0, 0 times 1, 1. Okay, I obtain this matrix. Okay, and then I can consider the states of my A and B subsystem separately. And in order to do so, what I need to do, in order to obtain the density matrix of row A, I need this trace over B. And what I should do, so I should multiply by my vectors from my B space in this case. And what I will obtain, I obtain this matrix. So you see that actually, if I consider my original state, it has a form like, so there are 4 components, like something times 0, 0 plus something times 0, 0 times 1, 1 plus something times 1, 1 times 0, 0 and something 1, 1 times 1, 1. Okay, and then I multiply it by for example 0, 0 times 0, 0 in a subsystem. What you will see that these 2 guys will die because here I have 1, 0 and here I have 1, and so they will die. And the same story about, and actually when I multiply it by 0, actually all these 3 terms will die. Okay, and then I multiply it by 1. Yes, then this term will die, these 2 terms will die, and the last term will survive. And finally, I obtain my density matrix, which lives in the A subsystem, in the space of A subsystem. And the similar story is about trace over B, over A, sorry, to obtain a state of a B subsystem. So it appears that it has the same matrix. And the important moment here is that it appears that this density, so this matrices correspond to a mixed state. Yes, and actually it's a feature. It's a feature of what is called entangled states. So you see that the original state was pure, but after I considered my states of my subsystem, they become mixed, and so it's actually it is a case for what is called entangled states, because you see that. So, for example, if my original state was, for example, of the form like, I don't know, phi, I'm sorry, like phi times he, okay. Yeah, for example, it's in the A subsystem, it's in the B subsystem. You can easily see that the density matrix of your A subsystem will be given just by phi A, and your density matrix of your second subsystem will be given by he. Okay. So it's what is called a separable state, because it can be factorized, yes, in 2 terms, And entangled means that you cannot factorize it like this one. And it's a feature. So we will discuss it more in detail. This stuff. So it's just yes. So you cannot decompose it just like something in A times something in B. You need these terms, 2 terms at least. Okay, and this is what is called the Schmidt rank. So the Schmidt rank of this state is equal to 2 because you need 2 terms to describe it. Okay, and the states where the Schmidt rank is larger than 1 is the untangled. So we'll discuss. Okay, so here I would like to somehow to give you this intuition of this partial trace, because sometimes it's not so easy, maybe so straightforward. And nevertheless, I hope that you somehow feel it. Now, so anyway, some questions about this stuff? No questions. So everything is okay. Well, great. I'm happy. Well, so then we come to the next, probably the last topic in this general overview of quantum mechanics is a story about evolution, of course. Yeah. So what we consider here, we consider what is called an evolution of closed system. What does it mean? So it means that I have some quantum particle, quantum system. It somehow evolves, and it does not interact with some other quantum particles, which is why it was closed. So as you know, so the basic, some very, very basic thing about evolution of quantum system is Schrödinger equation. So actually, all the other types of equations or master equations, blah blah blah, they all come from the Schrödinger equation because it's a core for all studies of evolution. So this is a Schrödinger equation. So you see that it's standard linear differential equation. So E times H bar times derivative of our vector is equal to the action of some linear operator times this vector. Okay, and usually in this science we will choose our units in such a way that our Planck constant is equal to 1. So we work with like dimensionless elements. Okay, and so this H, as you know, it's Hamiltonian, and also it's in the observable. The same, so it's on the one hand it determines your evolution. On the other hand, it's your observable of your energy. Okay, well, so that's it. Yeah.
As I remember, in the Schrödinger picture, observables do not depend on time.
Each observable do not in time. Why? Why? Actually, actually, it's not the case. Actually, in general case, it's a case that both your Hamiltonian and your let's say state, it evolves in time. So you are right in the sense that so your observable do not. So okay, so maybe let me provide some example. So, for example, we can consider let's say one half particle, one half spin particle. Okay, with a Hamiltonian like. Let me just use it H, like H omega times, I don't know, 1/2 over sigma z, which corresponds to the fact that you have two levels, okay, of your particle with the separation of your levels given by this H omega. And for example, you have some external field, okay, and it can depend on time. it's okay. It can depend on time. You have some dipole interaction, some dipole moment of your atom, and the full Hamiltonian looks like this, and it's okay. And there is no, so nobody prevents you to use this equation in order to describe this evolution, and it's okay. So this story about that, so there is Heisenberg picture, there is Schrödinger picture. So actually we will consider it now. Yep.
У нас есть система стационарная и нестационарная система. То, что мы, ну, который гамильтониан зависит от времени, который не зависит. А то, что представление меняем, она не становится стационарной или нестационарной. Просто есть система нестационарная, в которой гамильтониан зависит от времени. Даже представление Шрёдингера будет зависеть от времени.
Yes.
Наверное, утверждение такое, что мы всегда можем временную зависимость все функции перекинуть в гамильтониан, и все функции мы можем всегда сделать ее независимой от времени. А вот с гамильтонианом мы не всегда можем зависимость от времени перекинуть в любую секунду.
Actually, yes. So let us first consider the Schrödinger equation, then Heisenberg representation, then interaction representation, and then discuss it once again. I think we will understand more. Okay. So actually, the case where this H, this Hamiltonian, does not depend on time, is the more convenient one. And usually people consider it. Unfortunately, it's not always the case. However, okay. So let me put it here. Okay. So let my Hamiltonian be time independent. Okay. And in this case, what I can do, I can find the eigenvectors and eigenvalues of my Hamiltonian, and maybe so in order to find them, of course, you need to solve this kind of equation. And actually, this kind of equation is a very basic equation that people usually solve in standard courses of quantum mechanics. Yes, you remember these stories about harmonic oscillators, particles in wells with infinite size, and so on. Okay, and again, the reason why people would like to find this eigenvalues and eigenvectors of the Hamiltonian is the following: that actually they allows you to obtain an evolution for arbitrary initial state, and the idea, let us just I hope everybody of course knows this stuff, but nevertheless let us consider it once again. So if I consider, for example, consider evolution of my, I consider what is called an ansatz. I consider evolution of my system in such a form where my state is always is proportional to some constant times some eigenvalue. Okay, and if I put this ansatz in my Schrödinger equation, what I obtain? I obtain that I have this derivative of my coefficient, and actually I come to the equation on this coefficient, and I obtain the standard form that this coefficient evolves in such a form, yes, where I have this initial value of this coefficient, and I obtain this phase rotation of this coefficient with time, and the frequency of this rotation is given by this eigenvalue, which comes from the action of my Hamiltonian on my eigenvector. Okay, and then if I consider some arbitrary initial state, which I can decompose into the set of these eigenvectors, then from linearity I obtain that so the evolution of my initial state, where this coefficients, this coefficient Ci's can be obtained just from a scalar product of my initial state psi times this eigenvector. Okay, and then just from linearity, so because I know how evolves each component of this sum, I obtain the evolution of the whole sum, And what I obtain, I obtain the evolution in this form. So this is my initial value of my coefficient, which corresponds to this eigenvector phi I, and I obtain this phase factor, which corresponds to this rotation. And you see that so all different coefficients, they evolve with different frequencies, and I obtain some some evolution. Okay, and actually I can rearrange the coefficients, rearrange this construction in such a form where I have this psi, which is actually it's not it's psi naught, so it's initial state of my system. Okay, so yep, and here I obtain this kind of construction, and this construction, which is called an evolution operator. Okay, and it's given by this exponent of the Hamiltonian. So this huge construction is given exponent times this I times H times T, yes, which is called an evolution operator. And here is a maybe a bit non-trivial story about how to compute function. So you see that, so I have this H is an operator, and then I compute exponent of my operator, and so it's kind of non-trivial stuff. What is how to compute an exponent from matrices. However, so the basic idea is that you can use your Taylor expansion, so you can think about exponents just as a some Taylor series, and where you have only summation, some multiplications. Okay, and then you can put your operator in this expression, and this is how you can make exponents not from matrices. You can some people, so there are, for example, exponents of your super operators, which are operators which act on operators, and it's okay. Yeah, so you can compute exponent for anything for which you can which has this summation and have this multiplication operator. Okay, and here is actually again in your self-check assignment there is a problem on how to, so it's a problem how to derive the calculation of a function of a Hermitian matrix, and here is just some general rule. So again, so if you have some matrix, okay, some matrix A, and here it has some spectral decomposition. So this HI's are eigenvalues. So again, HI times HJ, it's a Kronecker symbol, and again A times HI gives you lambda I times HI. Okay, so it's our eigenvalues and eigenvectors. So if you would like to compute a function, what you should do, you should replace this your eigenvalues with the functions of your eigenvalues. So it's a general rule. It's how you can compute your function. Okay, and also important fact about this stuff is that you see that your eigenvectors for your function and here for your original operator are the same. That is why the commutator of your matrix and your function of a matrix is the same. Okay, so they always compute, and sometimes it's important because you can swap it as you like. Okay. So again, the general idea is that you obtain your evolution operator in this form, and it's nice. So you have this unitary operator, and in order to obtain your psi vector at some times t, what you need, you just to multiply your evolution operator, okay, times this vector at 0 moment. Okay. Well, any questions about this stuff? Yep.
Function that we can apply to an operator is some trivial function.
I think what you need convergence of your Taylor's decomposition. Yes. So, as I think, exponent, sine, cosine, they are okay. So I think about function which I cannot compute, and I cannot imagine. Yes, it's a kind of.
Ну, сходимость, например, сходимость матричных.
Yeah. So which kind of norm do you use? So here we have some, I think Hilbert-Schmidt. So here we use some Hilbert-Schmidt norm. Well, good question. So it looks like if I take every analytical function, so if I have some function, okay, and I can decompose it into Taylor series, so I started to think about Laurent series. So if it's okay, honestly, I need to think. I don't know. So usually all standard functions are okay, but I'm not sure that there is some kind of non-trivial example, some sophisticated function which you cannot compute, for which you cannot compute your metrics. Actually, so look, you have your original function, you have your metrics, okay? And in order to compute a function of your metrics, what you need, you need to compute your function of your eigenvalues, okay? So eigenvalues are real values, okay? So the only bad case, for example, may be, for example, if this guy goes to zero, for example, if this guy goes to infinity, okay? So for example, yes, for example, actually it's the case. For example, if I the standard situation, I have my pure state like this one, yes. I some row, and for example, we will speak about some phoneme and entropy, and in phoneme and entropy, you need to calculate logarithm of row, yes. And if you would like to compute this logarithm of this function or this row, you will see that you have some problems because you need to calculate your logarithm of 0. And
yeah, but there's always row logarithm row.
But however, yes, there are row logarithm row, and so actually you need to compute not logarithm row, but let's say lambda logarithm lambda, and there is some convention that it's equal to 0 if your lambda is equal to 0, because it converges if your lambda goes to 0. But so if you have so it depends on your spectrum, yes. So the answer is that the fact that you can compute your function of your metrics, it's closely related to the fact that you can compute your function for all your eigenvalues of your metrics. If it is the case, that no problem. If it is not the case, there is a problem. You cannot compute it. So this is the case. Okay. Well, so and at which time we should end? 20 minutes. 20 minutes I have. Okay. Okay, I have 20 minutes. Okay. Well, so what is so this is what's the easiest case, and the thing which I think we should to consider is a case where, so let us then imagine that our Hamiltonian is time dependent, and in this case I obtain I come to some problems, and so if you look at your evolution operator, it has this simple form, and you're saying, okay, so what about the case where my Hamiltonian start to depend on time t? Yes, and you can think as well, okay, it looks like that my evolution operator should looks like this way. Yes, so I should replace my summation over some integration, but however, it's not the case generally. Yes, so but generally. Okay. So, and let me explain why it is so. So the idea is the following: that imagine that we have this kind of evolution where this is time, okay, and for a time for, let's say, from 0 to tau, yes, I have my evolution which is described by Hamiltonian H1, and this Hamiltonian is time independent. It's okay. And from time equal from tau to 2 tau, I have my Hamiltonian equal to H2, okay, which also does not depend on time. It's okay. And then in order to obtain my state at the time moment to tau, what I can do, I can apply 2 evolution operators. So look, that first I should apply the evolution of operator on which is with H1, yes, and then I should apply the evolution operator with H2. Yes, and it's really true. It's correct. But however, generally, if my H1 and H2 does not compute, I cannot write it in this form. So I cannot put this to H1 and 2 in one exponent. Yes, because here is a matrix. Here we work with matrices, with operators, but not with the scalars. And in order to compute exponents, we need to use this what is called Baker-Campbell-Hausdorff formula. So I even didn't write it by my side. I just copied from Wikipedia. So what is a general idea? So if you, for example, you have this some e times x plus y, so you see that there is a huge expression, and in this expression, so first you have okay. So you have these two terms, yes, just x and y, and then you have a number of terms with these different kinds of commutators in such a way, okay, and so it's like an infinite sum. So, and of course, if you in a commutative case where your commutator is equal to 0, of course, all these terms will die, and you obtain your simple expression. However, in non-commutative case, you have this disastrous formula, and the same is for if you would like to, like in opposite, you would like to compute your two exponents. Yes, so your resulting matrix, your resulting operator is given by this huge sum. Again, this x plus y, and then you see this is a kind of a lot of different commutators comes in. Okay, and this is the reason why this naive way of thinking doesn't work. So you cannot just calculate your integral and obtain the result. You need some more sophisticated stuff, which is what is called t exponent or time ordering exponent. So I didn't derive it here because we will not use it in our course. I think in this lecture notes I will add a reference on a nice it's a paper. It's like also a piece of lecture course where this time exponent is derived. It's not very difficult, but it's not, I think it's not trivial. It was actually yes, there is a kind of summation. Yes, you maybe just a second. I will find it. Just I will copy paste because I do not remember this kind of. It's really okay. Just a second. It was called. Okay, well, so this construction has the following form. It's called the Dyson series. This has the following construction. It's identity operator times the summation over infinite number of terms. Here I have this I divided by h in general case time n, and there is a set of integrals from 0 to t1 dt1, then an integral from t0. Oh, it's actually not t, so in our case it will be just 0, from 0 to 2 times dt2 times blah blah blah. And here is finally from 0 to tn, where remember this tn goes to infinity, and dtn, just a second, and here I have my h at the moment t1 times h of the moment t2 times blah 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 h of the moment tn, and this is, so this is the expression.
Она должна до следующего интегрироваться. То есть Т2 до Т1, Т1 до
Т. Sorry, yes, yep. So in this, of course, yes, thank you. So in the first, you have this T, and here we have T1, and here is Tn minus 1. Yes, of course. Yeah, this way. Okay, and this is a full expression for this stuff. Okay, and actually, what is how it also can be G2? Just a second. So let me write it maybe in the following. So also people can, so people introduce it with what is called time ordering operator, and then it can be written in a more maybe easier form. So we have the summation where n factorial. Here we have I over. So actually, because I rewrite it from other notes where people do not use this convention. So here, so in our notes we use this h equal to 1, and actually if you do not if you will keep your h bar, so what you will obtain here is you will obtain here this 1 over h. Okay, so in our notation we can just put we just can remove it and put it like 1. Okay, then this will be okay. So here I just, because I rewrite this result, and then you have the summation, and then you have a bunch of integrals. Yes. So actually, so in our case, well, if we go to classical limit, like.
Ну, то есть у нас же n стремится к бесконечности, ну, как бы 1h в степени n, а n стремится к бесконечности, то есть мы по n стремимся.
Okay.
Значит,
ну, у нас вот это вот 1 на маленькое число вытратить, и мы будем...
So you have this n factorial.
Okay.
So it's okay. So I'm sorry. My it does not fill me. Well, sorry, some technical problems. It was too sophisticated for mine. Come on, man. Что за фигня? Кто помнит, как на iPad вывести этот вон. Окей. Все пропало. Так, сейчас. Okay. So let me write it in full form. So we have this from 0 dt1, from 0 again to 2 dt2 times blah 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 times from 0 to t again dtn, and here we have times sorry, come on man, h, and here is this what is called time ordering operator. Here I have this h times t1 times sorry, product h t1 h t2 times blah 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 h tn. Okay, and this operator is what is called time ordering operator, and so the idea is that like it's rearrange your Hamiltonians which are taken at different times in such a way that so first you have this like the earlier times, then yes, and then it's more. Okay, so you understand. Okay, so I will give the, so I will provide you with this nice derivation, because it's really not so. So we will not use it in our course. So you see that in general case the things are not so easy. So it's not so easy to write to obtain this this solution. Okay, and so anyway, the basic thing about our unitary operator, about our evolution operator, is that it's unitary. Yes, unitary, and unitary means that if you multiply your unitary operator times your operator dagger, then you obtained your identity matrix. Yes. So the way how you can think about unitarity is that unitary means reversible. Reversible. So you see that your evolution operator given by, let's say like this one in time independent case, if you go from your Hamiltonian to, let's say, minus Hamiltonian, which is also Hermitian metric, so it's okay. So it's allowed to have this minus h. Then you obtain your evolution operator like in backwards in time, like EH2. Okay, and so and it's U1 and it's U2, and it's just U1 dagger. Okay, so it's reversible. Okay. So this is a story about the Schrödinger picture. So again, so as you noted, it's very important that in this picture, what we have evolution of states. So we have some initial state, and we have some evolved state at some time t. And if you would like to compute some measure, some mean value, for example, or some probability to obtain some measurement outcome, then for example, for mean value, what you will obtain, in order to, for example, compute, I don't know, some observable, you need to put your matrix of your observable into sandwich of this psi vectors. Okay, which evolve in time. Okay, and really usually like a good observables, they do not depend on time. But however, for example, if you consider Hamiltonian, it's okay if it depends on time. But for example, if you consider like sigma x, sigma y, and sigma z, they, so for example, spin projections, yes, they do not depend on time. Okay, so in this picture, it's called Schrödinger picture. That's okay. And so the final story is that okay, we speak about matrices, about states, and for example, if we so we have time, yes, already. That's awesome. 3 minutes. Okay. So the final point is that okay, so my vector psi evolves as u evolution operator times psi. Okay, and if I consider my density matrix, which is like a mixture of some let's say phi I. Yes, of some states, then it evolves. So each of these components evolves with unitary metrics, and what we obtain that my matrix row evolves like U row U dagger. Yes, it's some standard story. And the basic evolution equation on a density matrix is given by this what is called von Neumann or Liouvillean von Liouvillean equation. It has the following form, that your derivative of your density matrix will be given by commutator of your Hamiltonian and your density matrix, and this is just corollary. So it's like a representation of Schrödinger equation for density matrices. Actually in my notes I tried to derive it explicitly. So if we consider a derivative of a density matrix, if you just compute it, then you will obtain this commutator. It's just some evident, some very easy thing. Okay, and so again, this evolution is given by this construction. Okay, and actually I didn't make an example. So I think it's a good point to stop. Next time we will start with a Heisenberg picture, and then with the interaction picture, and this will be the final part of this introduction in quantum mechanics or quantum computing. Да, давайте. Все, thank you very much. Все дела. Да. Так.
Можно его показать? Ну, там был этот примерчик, который 0,011 с весами 1/2.
Так, сейчас. 0,011 с весами 1/2.
Partial trace, вот.
Так.
Да. Ну, на самом-то деле, вот это дело, оно не лежит в тензорном произведении. Как бы.
Сейчас оно не лежит в тензорном произведении. Что значит не лежит?
Ну, у нас есть два пространства, мы их сконструировали неким образом.
Так.
Вот. А с чего мы взяли, что эта вещь может, короче, там лежать?
Сейчас, смотрите. Что такое тензорное произведение? Вот у меня...
мы просто по определению определили вот векторы, которые лежат в тензорном произведении, таким образом.
Да.
С помощью тензорного произведения.
Да.
Мы вот вообще можем найти разве два таких вектора, которые вот тензорное произведение, и получим вот такое?
Не, сейчас смотрите. Тут как
бы... я к чему? Потому что мы
не
получаем тензорное произведение, потом какое-то пространство.
Сейчас. В общем, утверждается, что вот эта штука я никогда не смогу получить как какой-нибудь такой.
Да.
Стоп идей.
Да.
Но это не означает, что этот вектор не лежит в пространстве тензорного произведения Гильбертова пространства. То есть по определению Гильбертова произведения Гильбертова пространства это новое пространство, которое натянуто на векторы, на базис на векторы, которые получаются путем тензорного произведения вот этих ребят. Дальше мы линейную комбинацию какую угодно.
Мы базисные векторы, в общем-то, сделали с ними. Да. А вот то, что там натянулось...
Натянулось, оно может быть любым, да. Так что все нормально. Да.
Отводят всякие истории, когда мы строим, а потом нужно дополнять пространство математически.
Окей. Нет, тут все. Что окей. Да, но он, конечно, векторизовать мы не можем. Так, что?
Да, еще такой вопрос. Всем по лекции, а вот там вот на конференции еще, вы, по-моему, задавали, я не понял ответа. Вот у меня описывают же квантовую систему этим уравнением, собственно говоря, либо Шрёдингера, либо Тарфман революции. А вот как вот с этим измерением связано? Измерение же тоже следует. Вот то, что он так
Так, это пипец сложная история. Короче, смотрите, есть два способа об этом думать. Первый способ, сохраняющий нервы. Значит, способ, который сохраняющий нервы. Он звучит следующим образом. У нас есть эволюция квантовой системы, которая, она квантовая, вот она как-то там что-то с ней происходит, да, и мы ее описываем раньше. Так? А дальше у нас есть отдельная сущность, отдельный процесс. Например, Пенроуз это называет, первую эволюцию называет U-процедурой, а вторую процедуру называют R-процедурой. Когда мы производим измерения, это совершенно другой тип эволюции, когда происходит этот коллапс. Это особый тип эволюции, который соответствует взаимодействию макроскопического прибора с микроскопическим объектом. Да. И там происходит вот этот коллапс, и работает правило Борна. Это вот такой, типа, Ландавшиц стайл. Вот если открыть Ландавшица, начало, да, вот он вот так и говорит. Типа, и все, не парьтесь. Вот есть квантовая эволюция, есть взаимодействие объекта с макроскопическим прибором. Происходит типа как редукция, и с какой-то вероятностью мы получаем случайный исход. Это первый способ, как об этом думать, сохраняющий нервы. Он работает. Да. Второй вариант для людей, которые хотят широко мыслить. Он говорит, а что такое макроскопический прибор? Камон, ребята. Давайте мы все будем, и измерительный прибор, и все описывать квантомеханически. тогда оказывается, что действительно мы можем так мыслить. Мы можем описывать самих себя, измерительные приборы, систему. Мы можем описывать как бы с помощью квантовой механики. И тогда процесс наблюдения на самом деле будет описываться какой-то унитарной эволюцией, которая будет, ну, как будет гамильтониан, взаимодействие между прибором и системой, получится унитарная эволюция всей системы в целом, все нормально. Я можно так описать. Но в итоге получается, что результирующее состояние после такого рода эволюции, это получается запутанное состояние вида наблюдательный прибор плюс результат наблюдения. То есть как бы в этом случае измерение сводится к производству запутанного состояния такого между измерителем и между тем же объектом, который мы измеряем, и измерителем. И получается эффективно, получается то, что люди потом называют многомировой штукой. То есть получается, что Вселенная в этот момент, как бы волновая функция Вселенной превращается в суперпозицию волновой функции, в котором как бы существуют все исходы измерений, все возможные реакции измерительного прибора на это измерение. Как бы это
Большой код Шрёдингера.
огромный код Шрёдингера такой на всю Вселенную распространяется. Да. Ну, как бы нормально. Но просто нужно, но это подразумевает, что если какой-нибудь, не знаю, генерация квантового ключа, как бы вот каждая генерация квантового ключа, это соответствует тому, что порождается количество вселенных разное, 2 в степени n, где n это количество ключа, как минимум. Это нормально, да, вот так работает.
Ну, а потом они там не интерферируют друг с другом.
А в том-то и дело, что похоже, что не интерферируют, потому что эта запутанность, она захватывает внешние степени свободы и, в общем, по-видимому, необратимость нашего мира, которую мы все наблюдаем, она как раз связана с тем, что они не интерферируют. По-видимому, так. Но строго никто не может показать, что они, ну, что в какой-то момент они не могут вернуться обратно. Кто строго не показывал, но это такой эмпирический, кажется, не должно быть. Это типа источник необратимости в нашей Вселенной. Вот такая фигня.
Вот вопрос.
Давайте.
Почему вот это вот все описание, то есть это как-то совсем не очевидно было?
Что?
Есть,
вот про эту экспоненту?
Да.
Экспоненту я знаю, я понимаю, что это не очевидно. В общем, я скину ссылку.
То есть тут будет, наверное, история?
Ну, ссылка точно будет. Ну, вот, саму страницу. Ну, в общем, будет ссылка на страничку. В общем, не могу прямо сейчас скинуть, если скажете, куда. Я вам скину.
Строго же легко.
Так, сейчас.
Они уже как массив.
Так. Чё, куда жать? Сейчас надо, друзья, наверное, найти чё.
Да,
вот это, да? Так, сейчас. Сообщение. Вот. Значит, это ссылка, там очень user-friendly объяснение, как выводится тайм-экспонент, вот это порядочный экспонент, и там...
Я вообще
вот, там...
ничего не понимаю.
Вот.
Каким образом там они упорядочены?
Но, как хотите, в следующий раз выведем.
Если есть вопрос. Вот этот вот бред, что типа, ну мы вот тут, короче, ставим, берем, чтобы сначала который первый действует, потом второй, потом третий. Вот это вообще как типа, работает? Есть примеры? Есть, ну, типа, нужно примеры.
Не было КТП.
Да было, но там и были эти коммутаторы. Я все равно по-нормальному.
Позже, в случае, когда гамильтониан не коммутирует сам с собой в разные моменты времени, нет, нельзя. Это, к сожалению, вот
свойство. Мы тоже писали, в каждый момент времени должен коммутировать. Для того, чтобы не списывать эту формулу.
Ну, если он коммутирует сам с собой в каждый момент времени, то вообще все хорошо получается, и там получается просто...
То есть он коммутирует сам с собой, если только не зависит от времени,